Warning! The following section contains M or MA material, namely mathematical equations. If you find such material objectionable, please 1. Focus on the descriptive text. 2. Just view the equations as a form of hieroglyphics. 3. Let your eyes follow the sweeping forms of the symbols. And 4. Notice the variables and constants that influence models. Hooray! You're gonna finally use that calculus that you're forced to learn. The first equations depend on the conservation of momentum. Momentum is the mass of an object times its velocity. In the absence of external forces, the momentum of a system does not change. Several assumptions simplify the mathematical representation for the conservation of momentum and its influence on air, water, and ice movements. In such a case, the conservation of momentum simplifies to the three following differential equations, where v equals velocity in a north-south direction tangent to Earth, a equals Earth's mean radius, theta equals latitude, f equals the Coriolis parameter, rho equals density, inverted E equals the partial derivative, P equals pressure or force per unit area, lambda equals longitude, U equals the velocity in an east-west direction tangent to Earth, G equals gravitational acceleration, and Z equals altitude. Of course, most people would not consider these or any differential equations simple, but the equations are even more daunting without these assumptions. The main point is that these equations involve things to which most people can relate. Conservation of mass or energy dictates that during each time step, the mass or energy entering a grid box minus the mass or energy leaving the box equals changes to the mass or energy within the box. The continuity equation is a mathematical expression of the conservation of mass, where inverted E equals partial derivative, rho equals density, T equals time, A equals Earth's mean radius, phi equals latitude, lambda equals longitude, U equals the velocity in an east-west direction tangent to Earth, V equals the velocity in a north-south direction tangent to Earth, and W equals the velocity in a radial direction from Earth's center, and Z equals altitude. The first law of thermodynamics is a mathematical expression of the conservation of energy. C sub P is specific heat at a constant pressure. It's equal to the amount of energy required to change a substance's temperature by a given amount. D equals total derivative, T equals temperature, small t equals time, rho equals density, P equals pressure, Q equals the net heat gain. Together, these equations constitute the fundamental or primitive equations of fluid mechanics that are at the core of every GCM. Both atmosphere and ocean models incorporate versions of these equations, but the spatial scales are larger in the atmosphere because air is thinner than water, and the temporal scales are longer in oceans because of greater thermal inertia. In practice, solving these equations proves challenging. Despite these difficulties, climate modelers approximate solutions to these differential equations via several approaches. One approach, that of finite differences, examines changes in a variable such as temperature over small increments of space or time, instead of infinitesimal ones. Another approach for solving the differential equations is spectral transforms. This is the process that occurs during a spectral analysis of music. In a spectral analysis, any variable that changes periodically over space or time is approximated by a Fourier series, which is the sum of a sequence of sine and cosine functions. Equations based on sine and cosine functions are relatively easy to differentiate. When the dependent variables are well behaved, spectral methods converge to a solution faster than finite difference methods. On the other hand, spectral methods may fail when the dependent variables become poorly behaved, as is the case with liquid water and clouds and surface topography. Moreover, distributing calculations over a cluster of computers, parallel processing, is often more difficult for spectral methods than for finite difference ones. Many GCMs, such as the Hadley climate model, use finite difference methods. Other GCMs, such as that of the CCCMA, use spectral methods. Still others, as the community climate model, take advantage of both approaches, using finite differences for vertical and temporal dimensions and spectral transforms for horizontal dimensions. In summary, number 1, models are necessary to study processes that are too slow, too large, or too unique for direct observations. Number 2, GCMs exploit all the computer power available. Number 3, GCMs, global climate models, are based on relatively simple laws from physical sciences. Number 4, GCMs take two major approaches for solving the equations that describe changes in weather over time and space.